So the UKMT Senior Math Challenge from 2017 then, let's just go ahead and do it. Which of these is prime? Well, that ends in a 5, so no. That ends in a 6, so no. That could be, and if you were doing this paper in 2017, you'd, I think, very likely know that 2017 was actually prime, so you'd immediately underline it. Of course, this ends in an 8 and this ends in a 9, which means this can't be prime. This could be except 2 plus 1 plus 8. I think, sorry, 2 plus 1 plus 9, which will be the digits of this number, are divisible by 3, so that number has to be divisible by 3. The next prime number, I think, is 2027, just in case you're watching this in preparation for some future challenges. Last year, this thing did this. It's mass per unit length, so we're doing this divided by this. You can simplify that, and then you can times it both by 5 to get it over 100, which makes 65. So I think it's going to be this. The 5 inches arranged in different order. In the new arrangement, the sum of the first three is equal to the sum of the last three. Well, the sum of the first three, which will, for example, be these three, and the sum of the last three, if those are to be equal, because the middle digit is shared, we just need the first two and the last two to equal each other added up. So we're just looking for a couple of pairs of numbers in here that add up to make the same thing. And it's not that hard, I don't think, to find the pair 5 and 6 and 2 and 9, which both add to 11. So as long as we put 14 in the middle, I think we're absolutely fine. This one here, we could write this one fancily as 2017 squared over 2017 to make the denominators the same. And now we're just doing this minus this. And this is the first of many, many instances in this paper in which we will do difference of two squares, which will give us e, because this becomes 2017 plus 1 into 2017 minus 1, which is 2018 times 2016. And that will be our answer there. 1 light year is this. This is 1,000 is 10 to the 3, a million is 10 to the 6. So in total, sorry, it's come up now. In total, I think this is going to be times 10 to the 9 more than this, but also with a times 13.4 scale factor. So I can sort of see, without doing any more work, that 10 to the 12 is going to become 10 to the 15, 10 to the 21. So I think this becomes 6 times 10 to the 21, except you're also timesing by 13. Now, because all of these have 8s in them, I'm just going to assume that 6 times 13.4 is about 8, or is about 80 maybe, something like that. It's definitely more than 10, which means I'm going to have to donate another power of 10 to this, which is going to make it from, well, we said it was 21 before. So now I think it needs to be 22. So I think it will just be 8 times 10 to the 22 without actually doing too much calculation there. Okay, so I'm not going to do colors, I'm going to do numbers. If we color this number 1, color this number 2, we could also color this number 2 in the interest of being as efficient as possible. And then this can go back to being color number 1. Now this triangle is the problematic bit because it can't be color number 1 or color number 2, so it must be a color number 3, and then we can just go back to a 2 and a 1 maybe, or a 3, it doesn't matter back here. But here's a configuration that works with 3 colors. And again, because of this triangular section here, you cannot do this with 2 colors. So I think I've got an example of 3 working, and I'm pretty certain I can't do it with 2 because of that triangle. So 3 will be my answer. Root 8 is 2 root 2, and root 18 is 3 root 2. So these come together to make 6 root 2. We can just square both sides to find k, right? 36, and then times 2 is 72, so the answer is 72. 1 to the power minus 1 is 1 over 1 to the 1, which is 1 over 1, which is 1. This is 4 rooted, which is 2, flipped, which is a half, and a half is not an integer, so we can underline it and move on. So the number k here is representing all of these small rectangles. So there's a rectangle that's 1 times 2, and then one that's 2 times 3, and 4 times 5, and so on, all the way up to 8 times 9. So the biggest one is 8 times 9, so that must be this one here. So we'll call that 8 and 9, and the smallest one is 1 by 2, which must be this one here. And I think all we can do is work backwards there. There must be another 7 times 8 rectangle, which looks like it's this one, and there must be a 6 times 7 rectangle, which looks like it's this one, and now we can just see the height here is 15, and the width is 8, it is 16, so I think n is 15 to make a 15 by 16 rectangle. And not much more to say. I think I did number 10 in a super stupid way. I mean, I did a lot of questions from here in a super stupid way. But what I said was that this length is x, and this length is y. Already, I think this is dumb, but I wasn't prepared to do it again. Now, because this big rectangle is similar to each of these small 3, if we just call the scale factor k, we can call the shorter length, which is equivalent to this shorter length from the whole thing, as kx, and the shorter width as ky. Now we can set up a couple of equations here because we know that 3kx's make a y, and we also know that x equals ky. So if we rearrange this really quickly, we get this. And because of the x equals ky from here, we can put that k into here, We cross multiply and stuff and we get this, and then we can square root both sides and we get this, which means the ratio of x to y, which is the ratio of the short sides, is just 1 to root 3. You just swap over the numbers that are in front of them, so 1 to root 3 or root 3 to 1, because they're actually asking for y first. In any case, once you get to here, it can't be anything other than this, even if the numbers are slightly in the wrong order. But which they're not, just the question was written in another way to the way that I did it. Anyway, the teenagers Sam and Joe noticed the following facts about their ages. The difference between the squares of their ages. So for this person age S and this person J, difference between the squares is S squared minus J squared. And that's equal to 4 times the sum, which is 4 into S plus J. This is our second instance of noticing that we have a difference of two squares to do. So this will be S minus J into S plus J, which is great because S plus J can cancel both sides. S plus J can't be 0 unless they're both 0 years old, which doesn't really make any sense. I mean, it potentially does. Maybe it doesn't for the next bit. I don't know. Cancel these two things out, we get this. Now we look at the next bit. The sum of their ages is 8 times the difference between their ages. I guess they could be they're teenagers. Amazing. Let's read the second sentence of the question. That gets rid of the 0, 0 problem. Anyway, we get this from the second sentence, but we know S minus J is 4 from the maths we did earlier, so that becomes a 4, which makes this a 32. And then we have that they both add to 32. And then this is just here and here. We can add these together to get rid of J. So 2S is 36, so S is 18, and then J was 14, but the older one is 18. The diagram shows a square and a regular decagon, so that's 10 sides, I believe. So 360 divided by 10 is an exterior angle of 36, which gives an interior angle of 1/4, which you may have just gone into this, exam just memorizing, which would be good. It's good to memorize those sorts of things. The key places to put 1/4 are here and here, I think, because that makes this one, well, we knew this one was 36 anyway, it's the exterior angle, but this one, crucially, is 360 minus this minus 90. And now at this point, I'm just going to start cheating. I can't be bothered to do 360 minus this minus 90. But I know whatever I do when I get that is something that ends in a 6. So I've just put ... 6. This angle definitely ends in a 6. Now, if we look at this shape here, I think it has 5 sides. I couldn't be bothered to count. We know the sum of the interior angles has got to end in a 0. Now, this ends in a 6, this ends in a 6. So currently, when we add up all these angles, we end in a 2. Now, that's a 270, which ends in a 0. That's a 0, which means I think x, to make the whole thing add to something that ends in a 0, x has to end in an 8, which I've already underlined. It's 18. And I can't be bothered to do any more maths than that. But I think to make the digits make any sense, I think x has to end in 18, and there's only one option that ends in an 8, which is, yeah, so I just kind of cheated there, but okay. We get the classic truth-lying question. Only one person is lying. Now, we just run through these. If Isabel is lying, that means Josh is guilty. But if Josh were guilty, he'd also be lying. If Isabel's lying, she's the guilty one, and there's only one guilty one. So that doesn't, it's already a contradiction. So Isabel can't be the one who's guilty. If Jonathan was guilty, then Tegan would obviously be innocent, which we know they are because that's how the game works. There's only one guilty person. Tegan's telling the truth about Isabel, who's telling the truth about Josh, who's telling the truth about Jonathan. So that's all consistent. Now, technically, we should probably run through the other two because it's possible that two people make sense, and then the answer would be E. More information is required, but it's not consistent for either of these two. If you try it, Josh says this person is guilty. Now, if he's lying because he's guilty, then that means this person is innocent, which means she's telling the truth or he's telling the truth, whatever this person is. But that doesn't work because Tegan isn't guilty because we're already assuming Josh is. And likewise, you can test the last one yourself, but it's not going to work. There's probably smarter ways of doing number 4 than what I did, but what I said was that this is a pentagon here, which has a sum of 540. I just know that. You can work it out if you want to, which means this angle here is 540 minus 4 x's, and that's this angle here. Now, this angle here is 180 minus this, because this is a straight line. 180 minus all of that is 4x minus 360. So that's this angle here, which is the same as this angle here. So this whole angle, excluding all this bit, and I could have just done 360 minus this, but this whole angle is just this plus itself plus this, which makes, I think, this angle here. So that angle there represents all of this. Again, I could have just done 360 minus this one, because this is the same as this one, and then 360 minus would get all this, but I didn't think of that at the time. So this angle here represents this plus this plus this. I mean, essentially, you just get 8x's minus 4x's, 4x's, and then 2 of those is minus 720, but one plus one of those makes a minus 180, so it's just this. Now, we look at the entire shape all the way around, which I believe is a 1, 2, 3, 4, 5, and then 6-sided shape. So the sum of those angles is 720. And 720 must equal this angle we just got, this big one here, plus 1, 2, 3, 4, 5 x's. And that must equal 720. And now we can just solve for x, and we're all good to go as 100. Good. Question number 15 then. So label the things they wanted us to label on the thing. And again, I don't think this is the best way of doing this question, but I called this length TQX. Now, because this is a square, I now have a side length of this square as x plus 1, which means for this to actually make sense, this length here needs to be x minus 1, again, to make this whole length here x plus 1. This plus 2 is x plus 1. And likewise, this needs to be x minus 2 to make the same thing happen, and this needs to be x minus 3. Now, what I did here was I said, well, okay, the area of the full square is x plus 1 times x plus 1, which is this. Now, what about the area of TUVW? Now, they're saying that's half of the whole square, which means the other half of the area is found in these 4 triangles. Which means if I just add up the areas of these 4 triangles, I should get half of this, which is the whole area. And I think that's what I'm essentially going to do. So each of the triangles is a half times the 2 lengths. So I just factorize that half properly. This 2x just refers to this times this. This 3x minus 3 refers to this times this. Then this 4x minus 8 is this times this. And then this last one is just this. And again, all of those need halving because they're triangles, but I'll just halve them all at the end. And then I'm adding them all together. I'm just doing this in a stupid order. But all the algebra should check out. I'm just doing this plus this plus this plus this algebraically, and I just get this, which you will do even if you do it in a more sensible algebraic way. Anyway, I've claimed that, of course, that this is half of this. So now I can double both sides, which gets me back to here, but whatever. And now I can solve this for x, which ends up being pretty straightforward. So x is either 3, which doesn't make any sense, because if x was 3, then this would be 0, which is not a thing. So x, I think, is 5, and we'll go with the length of PQ being 1 plus 5, which is 6. And yeah, let's have it there. Good. Okay, so this is a right-angled triangle. So 15 plus 20 squared, sorry, 15 squared plus 20 squared, you might just know as 25. And it must be 25 because I've done some other stuff there, but I'll explain in a second. Because it's just the 3, 4, 5 triangle times up by factor 5. Now, if this is angle x, this is also angle x because it's alternate angles. And then this side is 20 because this is a square overall. So this whole side is 20. Now this side, as I said, was 25. But the fact that this is x and this is x means these 2 triangles are similar. So I think we can find a scale factor from the smaller triangle to the bigger triangle. Now the hypotenuses go from 20 to 25. So the scale factor must be 5 over 4. Because I think 20 times 5 over 4, 20 divided by 4 is 5, times 5 is 25. So the scale factor is 5 over 4. Which means the scale factor in the other direction is, of course, 4 over 5. So to get this length here, which is the one opposite x, I think we can times this by 4 over 5, which gets you 16. And then we have more nice Pythagorean triples here. This length here is this squared minus this squared. But this, again, is just the 3, 4, 5 triangle scaled up by factor 4 this time. It must be another scale factor of 3, 4, 5 because it's similar to the other one, which was also a scale factor of 3, 4, 5. So that's cool. So this is 12, which means this is 13. And this is 20 because it's just a side length of the square. And this down here is 5 because 5 plus 15 make 20. And the area of this grey shape here, which is what they're asking, we can just split into this triangle and this triangle. So we're going to have to do 20 times 5 halved, which is just 10 times 5, which is 50. And 16 times 13 halved, which is just 8 times 13. And again, so lazy. 8 times 3 is 4. So this ends in a 4. When you add 50, it still ends in a 4. There's only one that ends in a 4. So without doing any more maths, I'm just going to say it's that answer there. 17 is, I've said I've done a couple of questions really stupidly. This is the stupidest of perhaps all of them. There might be one more coming up that's even dumber than this. But I just couldn't be bothered with this question at all. Let's call the number of sweets Amy has A. Now, she gives 1/3 of them to Beth. So I'm immediately going to cross this out and call the number of sweets Amy has 3A. Because then I can give 1/3 of them away easily, because 1/3 of them is just A. So, okay, let's then say Beth has B sweets, and now that Amy's given her 1/3 of hers, Beth has B plus A sweets. But then she gives 1/3 of them to Claire, and I can't be bothered to third this. So I'm going to go back to the start and say, well, since I have to third A twice, essentially, let's call A 9A. But then I read ahead because I knew that I didn't want to start again. And 1/3 of Claire's goes somewhere else. So we're going to end up having to third Amy's sweets 3 times. So I just went ahead and called Amy's sweets 27A. Just that I really wouldn't have to work with any fractions because I couldn't be bothered. So let's call Amy's sweets 27A. 1/3 of them go to Beth. 1/3 of 27A is 9A. And I'm going to call Beth's sweets 3B because I see that a third of them are going to have to go to Claire. So a third of this is B plus 3A, which go to Claire, who I'll call C, and then B plus 3A go to her as well. So now Claire has this many sweets. But then a third of those go to Amy. So then I realized I was really, really dumb because for the same logic that the A's third 3 times, the B's third twice, and so do the C's actually. So let's go right from the very start. I don't know why this is typed out twice. And that was just me copying, pasting, and then deciding to start somewhere else. So Amy has 27 A suites. Let's start with Beth having 9B of them. Now, Amy's third go to Beth. A third of this is 9A, so Beth now has this. Claire will start with 3C suites, and a third of this is 3B plus 3A, so that goes to her. And then a third of this goes back to Amy. A third of this, of course, is just C plus B plus A. Amy, after having given 9A of them to someone else, has 18A, so she has now at the end 18A plus a third of this, which is C plus B plus A. So that's how many Amy has at the end. Now, they all have the same number of suites at the end. So Amy's finishing amount is the same as Beth and Claire's finishing amounts. Claire's finishing amount is this, because it's just this one minus the 1/3 of it. And Beth's finishing amount is this, again, minus 1/3 of it, which is this here. So these amounts are all the same. But also, Claire begins with 40 sweets. Now, this is where I swore and punched the wall, because I started with Claire having 3C, which is apparently now equal to 40. So despite all of my restarts and trying to be smart about this, I found C is 40 over 3. So I have to work with fractions anyway. And at this point, I absolutely couldn't be bothered to restart this with a number that would actually be divisible by 40. So I don't care. C is 40 over 3. Let's substitute this into these two equations. I'm just doing these two. I'm not doing the triple bit, just these two here. Put the C in there, you get this. And now if you put the C in here, you get this. And now this looks like a simultaneous equation in A and B. So I'm just going to plow through this and solve this because I can't be bothered to start again. So if we write this in a slightly more intelligent way, we get this. And write this, just divide everything by 2, you get this. And now I'm looking for how many sweets Beth has originally. So I need to find 9B, if you remember. That was how I called Beth originally. So, okay, well, finding 9B from here seems frustrating. I mean, adding these together is great because then you find the A's instantly. This plus this is 60 over 3, which is just 20. So that's just this added together, which, I mean, I think I can then work through this fairly sensibly. I mean, A is this, I guess. And then I can put that in here. And now, remember, I'm looking for 9B, because that's Beth's original amount. So if I times this by 9, I'll get this. And then, of course, 9A is just 10. So that becomes a 10. Take it away from both sides and get 9B is 50, which will be how many Beth has. Please don't bother writing in the comments just how dumb that method was, because I'm fully aware of just how dumb that method was, and I don't care. So that's fine. Question number 18 is talking about the arithmetic and geometric mean. Now, arithmetic mean is this, and geometric mean is that. So the way that you set up ratios like this, nice little trick, which I just did instantly, was this over 5 equals this over 4. That's just a way of dealing with ratios and making one equation from them is left over left equals right over right. So now we can cross multiply and we get this. Now, that doesn't seem amazingly helpful. What's the only thing you could do with this that might make progress? Well, I don't like root x, y's, so I'm just going to square both sides. Now, you need to square everything, right? So this squares to 4, this squares to itself squared, this squares to 25, and that squares to xy. Now, why does this work in any way? Well, if you actually expand out this left-hand side, you get this. And now if you take away 25xy, you get this. And you might notice that that actually does factorize. It factorizes to that, which means either 4x equals y or x equals 4y, which you can then solve to make these two things. Now, x is bigger than y, and they're both positive, which means I think this has to be the thing. And now if x equals 4y, then that means the ratio is 4 to 1. Again, just swapping over the numbers like we did a few questions ago, and we're good. Now, I couldn't work out how to do 19 properly, so I just cheated. And when you don't know how to do, firstly, it's a 2 by 4 rectangle, so it's 2 here and 4 here. So that's 2 as the circle, which means the radius is up as 1. Now, if you can't think or work out how to do a question geometrically, a nice backup plan that you should always have in your mind is, what if I just did this as a coordinate geometry question? So what if I just put some axes on the picture and just decided that rather than things being shapes, everything would just be an equation of a line or whatever. So the equation of the line that goes through PQ, because it goes across 4 and up 2 and goes through the origin that I invented, is just the equation y equals a half x. And the equation of this circle here, because it has center 1, 1, and radius 1, is just x minus 1 all squared, blah, 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 blah. And if I just find the intersections between these things, that will be the coordinates of P and Q, which I could then do some Pythagoras on to find the distance PQ. Now, this is a massively... I haven't read the mark scheme carefully enough to know if there's a actually good way of doing this question. I imagine there is, but I'm quite fast with algebra, so I'm not too worried about taking the time loss on this. I'm just going to put this thing in here, expand out very carefully, and then obviously combine terms. I think I'll times everything by 4 at some point to get rid of this fraction. And this actually factorizes, which is very nice. If it didn't, I'd be a bit annoyed and the rest of the maths would be very difficult. But it ends up having answers this and this, which is very easy to find the y coordinates for because this equation is quite easy to work with. And now I just need to find the distance between these two coordinates, if these are the two intersection points. So in terms of x, it goes across from 0.4 to 2. So it goes across 1.6, and in y's, it goes up 0.8. Now, I could do Pythagoras on this triangle, but I still can't be bothered to do that because I don't want to square those numbers. Fundamentally, this is a right angled triangle that has a base twice as big as its height. So it's very fundamentally the same as this triangle. This triangle clearly has hypotenuse root 5 by Pythagoras, which means by a scale factor, the scale factor here is times by 0.8, or because 0.8 is 4/5, times by 4/5. This hypotenuse must be 4/5 root 5. And if you unrationalize that, you end up with answer B, because if you times this by root 5 and root 5, you get to this here. So yeah, we'll end up with the answer of B. Number 20 then, side length of square is 1. Now, if we do a little bit of Pythagoras on the inside of this square here, we can find its length across is root 2. Now, that's really important because it says that URT is an arc, which means it's a sector of a circle centered at P. So if this radius is root 2 then, of a quarter circle centered at P, that means this distance is root 2, which means this distance here, this little one here, is root 2 minus 1. Right, because that whole thing is root 2, because that whole thing is just a radius of a thing. And now we can just work out all the areas separately. So I think this is just me doing that there. So, sorry, the perimeters separately. So this here looks to me like it's a quarter of 2 times pi times r, where r is root 2. So that's the arc length URT, a quarter of the circle with radius root 2, 2 times pi times r, and a quarter of it. This is the same one, but down here. This here is the arc length of this little circle here with a quarter of it as well, and this is the radius root 2 minus 1, and so is this. Now, of course, a quarter times 2 is 2, sorry, is a half, but then you add it to another copy, just makes 1, so this is just pi root 2, and likewise, very similarly, this is just pi root 2 minus 1, and if we put these together, we get 2 root 2 pi's minus pi's, which factorizes again to b, and we can underline b as our answer. 21 is a great question. You can probably instantly spot that x equals 2, y equals 1 is a solution. Now, y equals minus 1 is not, because we're looking for positive integers. If you just try the next one, so I mean, the answer is at least B, it's not A. If you try the next one, x equals 3 gives you 64, take away 15 is 49, and y equals 7 actually also works. Now, it seems pretty human to try the next one as well, just to see whether they all work, which would be this, but it doesn't. So how do we, I mean, the answer is this. I actually, at this point, thought the answer was definitely this or this. This seems like bait, because it's like, well, what if you didn't read this question and saw that and thought that you'd have 4 pairs with the minuses as well if you didn't read this word? So I thought that was bait. So I thought to myself, this is the answer or this is the answer. Which one seems more likely? I would have guessed this. It took me a few more minutes to work out how to actually get there. But 40x, a classic thing to do with 40x, which you can just try, is talking about it in terms of 2's. So this is 2 to the 2x, or 2 to the 2, or to the x. Now, of course, these two numbers multiply when you've got brackets like this, but a really nice little trick is to actually, instead of multiplying them, just claim that multiplication works both ways around, so instead just swap them over. And now we end up with something squared. And here is something else squared. And this should trigger something instantly in your mind of, well, I've got a couple of things squared here. So what if I put them on the same side? Oh, difference of 2 squares. Incredible. This is, I think, the last time we're going to use difference of 2 squares here. But difference of 2 squares again. And because these are all positive integers, that means that we're just looking for factors of 15, which can only be 1 times 15. It's pretty logical that this is going to be the smaller one and this is the bigger one. 1 times 15 or 3 times 5, which means there are actually only 2 pairs that do this. So the answer is C. Of course, if I just show that if this one was a 1 and this was a 15, you of course end up with this pair, because if you do this, take away this, you get 2y is 14, so y is 7, and then you get x is 3, and then the other one refers to this solution here. So yeah, there are two answers. Really lovely question, I thought. So we've got a square with edge length 1. So of course that means this length is root 2, as we've seen before in this paper. I don't really care about that. I'm going to halve that down and say the distance from the center to the edge is root 2 over 2. Just halving that whole hypotenuse down, which means that, of course, this distance here is also root 2 over 2. And this angle here, because there are 8 sides, is 360 divided by 8, which is 45. So I think I can instantly answer this question if I just work out the area of one of these triangles, which is a half times this times itself times sine 45, all of which I can do. I'm confident I can do that. And then just times the answer by 8, because there are 8 of these triangles. So that's what I did. Sine 45 is root 2 over 2. This thing squared is 2 over 4. And then basically everything cancels except for this root 2. And we end up with a root 2 as the answer. Really fun question, I thought, 23. Really instructive question as well, because y equals x squared is this curve here, and y equals x plus 2 is a line like this. Now, I'm going to say that I have absolutely no idea how to work out the equation of a curve that's reflected in a diagonal line like that. I know nothing about that. And I would hasten a guess, that's not good English, but I would, what's the word I was looking for? I would hazard a guess, maybe, that nobody or almost nobody watching this video knows anything about how to do that either. So when we're in this situation, we've got to think, okay, we've got to find a trick, right? I don't know anything about this. I don't think I'm expected to know anything about this. I mean, the curve looks like it's something like this, right? I don't know anything about this. I'm not expected to know anything about this. So how can I do this anyway, even if I have no idea about any of the maths that is currently going on? Well, ask yourself, what is the only thing you do know about reflecting this curve in this line? The only thing that I know for sure is that whatever it looks like, this point and this point is preserved. Because when you reflect anything in a line, where that thing goes through the line stays where it is. So whatever my curve is, it definitely goes through this point and this point. So let's find those 2 points, right? Just set the curve equal to the line. It ends up being very easy. You just get this, which is this, and then you get the y's and you get this. So whatever my reflected curve is, it must go through the points 2, 4, and minus 1, 1. And then I can just test them all. Which one goes through both of those points, right? When x is 2 and y is 4, well, when y is 4, this is clearly going to make something much bigger than 2, so we'll get rid of that straight away. Again, when y is 4, this makes something much bigger than 2. When y is 4, this makes 16 minus 16 plus 2. Okay, so this checks out. Let's check the other one. When y is 1, you get 1 minus 4, which is minus 3, plus 2, which is minus 1. So this checks out for both points. So fantastic. So C is likely. It's possible that another point, a couple of these check out. And if that's the case, then I'm going to have to do something else to try and decide which one it is. So let's test the others. So when y is 4, you get 0 minus 2, so that doesn't work for the first point. And then when y is 4, this clearly doesn't work. So C is the only one that works. So they are being very kind to us. So C must be the answer because it's the only one that goes through both of those two invariant points is the word that you could maybe describe them as. 24 then. So again, I feel like they've asked questions similar to this before, and I feel like I suck at them every single time they ask them, and I don't learn anything from them at all. I would have just skipped this question if I was in the paper, in the same exam, and if I had time at the end, gone back to it. The only thing that I can do, that I sort of have picked up about questions like this, is that if you just draw a bunch of lines, they all intersect. Like if you have 3 of them, obviously they intersect 2 other lines because lines don't intersect themselves, right? So if you have 3 lines that are non-parallel, then they all intersect 2 because they all intersect all the lines other than themselves. So one way that we could get a set of lines to intersect 10 others is just draw 11 non-parallel lines. I couldn't be bothered to draw that, but if you just draw 11 lines all going in different directions, they'll all intersect 10 other lines, and you've satisfied the question. So we can cross out A because we can definitely do that. That at least takes me down to a 1 in 4 guess rather than a 1 in 5. Now, let's think of other situations we could do to change this. Because the key thing about this, of course, was parallelness or non-parallelness. So what if we decided to start introducing some parallel sides ideas? So for example, what if I drew 3 parallel lines and then 3 parallel lines going the other direction? Now, that means because all of these parallel lines that are kind of in their own group of parallelness never intersect each other, these are all kind of behaving as just one parallel line, as one line, except they give the other set of parallel lines opportunities to hit more things. If we just count these, of course, they all intersect three things. Every line here intersects three things, which is quite useful because we could sort of scale this idea up and say, well, okay, what if we therefore had 10 of them going this direction and 10 of them going the other direction? That would mean that all of these 10 wouldn't hit each other because they're all parallel, but they would hit all 10 of these. So that would be 10 intersections, and likewise vice versa. So every single one of these 20 lines would have 10 intersections. So therefore, I think 20 is something that I can do by just scaling this picture up. So, okay, this is the zero parallel line idea. This is the set where we've got two sets of parallel lines ideas, I guess. So what if we scaled it up to 3? So what if I said there were 3 like this? This is the classic airbase situation. Air bases used to be done like this to make wind direction. So why am I going off on this tangent? I don't know. Air bases used to be drawn like this so that whatever the direction of the wind, there would always be one landing where you could land into the wind, which is what you want to do when you're flying a plane. So Silverstone used to be an airbase that looked like this. Of all the tangents I've ever been on in my life while making these videos, I don't know why. That's probably the worst I've ever done. But anyway, what if we tried to set up the old Silverstone RAF airbase situation? So again, we can duplicate these parallel lines because that means they won't intersect each other, but they will intersect other things in the parallel line set. And again, this idea I think could scale up because what we could do is, what if we had 5 going in this direction, 5 going in this, and 5 going in that? Because if we did that, each of these parallel ones would intersect 10 because they do intersect these 5 and these 5. Each of these would intersect 10 because of these 5 and these 5, and each of these would because of those and those. So I think that would be 15 lines all intersecting 10. So I think I can do 15. And those are the ones that I managed to draw. And then I couldn't think of how to do the other 2. So I tried to look for a pattern here as to like, what is it about these that actually make them work, and therefore could I find one without drawing it that actually works here? So here we could think of this as 11 sets, each appearing at one time. So this is a set of lines going in this direction, but there's just one of them, and likewise this is. Whereas this is 2 sets. We've got the lines going this way and the lines going this way, each appearing 10 times. And this is 3 sets, each appearing 5 times. Now, how are we getting 10 out of this? 10 is the key number. Well, if you take away 1 from this, because that kind of refers to the fact that the line can't intersect itself, if you take away 1 from this, you get 10 times 1, which is 10. If you take away 1 from this, you get 1 times 10, which is 10. And if you take away 1 from this, you get 2 times 5, which is 10. The only other way to make 10 is to do 5 times 2, which again, because we're taking 1 away from this every time, would actually end up being 6 times 2. So I couldn't be bothered to draw it, but I think my logic says if I had 6 sets of parallel lines each appearing twice, then that would intersect 12 times. That would be 12 lines in total, each intersecting each other 10 times. So I think D is the one that I'm not going to be able to do by deduction, I guess. And 25 is a much nicer question. I feel like this is question 25 because the answers just look so horrendous that most people would just ignore it and don't even try, when it actually ends up being not a particularly hard question. So let's just call the side length of the bigger nonagon 1. And this angle here, of course, if we do 3, is the exterior angle of a nonagon. So 360 over 9 is, I think, 40. And that's obviously good because of all these 40s here. So we have a right angle triangle that looks like this. I'm going to work out both the base and the hypotenuse of this. The hypotenuse is just sine 40 is 1 over the hypotenuse, which means 1 over sine 40 is the hypotenuse. And this length here is, I think, we should probably use tan, right? So tan 40 is this over this. So this over tan 40 is this. Now, tan 40 is not appearing anywhere in the answers. So, and I know this seems a bit harsh for people who haven't done this maths yet, but I think I need to write tan 40 as sine over cos. And if it's 1 over sine over cos, that makes it cos over sine. So, okay, I think that's cos 40 over sine 40. Now, what am I going to do with this? Well, if I know this length here is cos 40 over sine 40, and this whole length here is 1 over sine 40, I think this little length here, which is the difference between the hypotenuse and the base, is this little length here, the side length of the nonagon. So let's do this length minus this length to get the little bit that's left over, which is, of course, this little bit here. This minus this, of course, the denominator is matched already, so it's just this. And that is the side length of the smaller nonagon. So now we have or we can find a scale factor, right? It's a scale factor from the bigger nonagon, which has side length 1, to the smaller one, which has side length this. We obviously just need to times by this, because we started at 1. 1 times this is, of course, this. So this is the scale factor from big to small. Now, we're talking about areas in this question here. So if the scale factor across length is this, that means the scale factor across area is this squared. So I think if we define the area of the nonagon n to just be n, I think n times this scale factor squared is the area of S, which I'll just call S. Now, of course, what is a fraction of the area n? It is S. I mean, what is this asking us? It's just asking us for S over n. So S over n is just this thing squared, right? So I literally just need to calculate this thing here. And I think I lied before when I said the last instance of a thing that we did a bunch of times in this paper had happened, because it hasn't actually. If we square top and bottom of this separately, I couldn't be bothered to square this out. In fact, no, that's a lie. I did square this out, and then I realized I shouldn't have, because sine squared of 40 is the same as 1 minus cos squared of 40. And now here is our last instance of difference to two squares. This is 1 squared minus cos squared. So it's 1 plus cos into 1 minus cos, and then these minuses cancel to leave you with one of the minuses on top and one of the pluses on bottom for the answer of A. And that's the whole paper done.